Hello everyone, I'm Jyoti from Microsoft and today I will be presenting a work on Query Optimizer as a service. This work was done jointly with Alek Jindal and is in submission at Sigmod Record. As you all know, query optimization is important for reducing cost of user queries. It is now becoming a critical piece in modern clouds where there is no database administrator and user expertise is minimal. We are seeing a lot of effort and investment in building advanced query optimization capabilities in systems such as Spark, Greenplum, Snowflake, Azure SQL, Scope, Spanner, among others. Unfortunately, the current approach to building query optimization capabilities results in re-implementing similar techniques in different systems again and again. For example, many systems including Spark, Cascade, Greenplum, SQL Server, and Scope have re-implemented cascade-style optimization. Instead, we proposed unifying query optimization capabilities into a common platform that will help serve the customers better by advancing state-of-the-art across the board. Apart from redundant effort across systems that we just saw, getting query optimization right just for a given system is hard by itself. This is evidenced by decades of research as shown in top left on improving strategies for query optimization. In fact, most production systems have been hardened over the years based on countless performance regressions seen by product teams over time, as shown in bottom left. This has also resulted in query optimizers turning into massive black boxes of legacy code that the product teams are highly skeptical to change significantly. Next, let us understand the cause of this problem, which is the tight coupling of the optimizer within the query engine. It is time to decouple the query optimizer from the query engine into a separate platform. We do this by externalizing query optimizer components to an external service. A key enabler for such externalization is the number of recent machine learning-based techniques to improve cardinality, cost model, and query planner. In the remainder of this talk, I will walk through steps we took towards realizing this architecture at Microsoft. Having understood the problems, consider an alternative service-oriented approach to query optimization, which we call Oysters, as shown in this slide. The first thing to notice is the externalization of three components of the query optimizer: cardinality estimator, cost model, and query planner from the deeply embedded query optimizer to an external service. Additionally, the externalized components are hosted as LearnML models trained over past query workloads seen by a given set of customers in a given environment. For each incoming query, relevant models are loaded to the query engine based on patterns in the query. The engine still contains its default optimizer. However, its components are overridden by learned models loaded from the external service. Next, I present a 7-step recipe for turning a query optimizer into optimizer as a service. First is creating signature or hashes for every query sub-expression. In figure at bottom, I showed two queries containing same signatures. A signature captures a query subpattern whose behavior could be learned across the entire workload. Therefore, it is extremely lightweight featureization, which is useful given the sub-second end-to-end time spent in query optimizers. Second ingredient is telemetry collection. The query engine needs to emit signatures along with runtime metrics to telemetry. It helps understand query performance and helps build better cardinality and cost models. The telemetry collected is used for generating training inputs for machine learning models. This step involves extracting the telemetry into a tabular structure and applying data cleaning techniques to it. And how do our models look like? Our models are micro models or lightweight per signature models. Micro models are small in size, thus faster to train. Micro models train the generality of traditional query optimizers, wherein they had to produce the exact same behavior for every query and every customer, with specialized behavior that is ultra-local to a given workload. Fifth is model lookup. For faster lookup, we load models by customers, query templates, or signatures. Sixth is in-process scoring within the query optimizer. This helps reduce the overhead of making thousands of external invocations for model scoring. We load models in the optimizer and score them whenever needed. Seventh is overriding default optimizer behavior. This can be done by checking presence of available models. This is one-time deep change in existing query optimizers that is useful to control behavior from externalized service. Next, we describe a success in deploying Optimizer as a service architecture for Cosmos Big Data Platform in Microsoft. In Cosmoscope query engine does batch processing in a job service form factor. It processes massive workloads consisting of hundreds of thousands of jobs each day, which are scripted by thousands of users and they process exabytes of data. If we look at cardinality estimation and scope, it could be off by orders of magnitude. This is due to user-defined operators that end up as black boxes for the query optimizer. Using the micromodel mechanism discussed earlier, we were able to achieve up to 6 orders of magnitudes more accuracy. There was significant effort to replace original cost model and scope as explained in Sigma 2020 paper. However, it had gaps in terms of production readiness. The externalized architecture of Optimizer as a service provides a solid foundation for iteratively improving these approaches. Next, moving to externalized query planning. The scope query planner consists of 256 rules, with one-third of the rules not enabled as described in the Sigma 2021 paper. Our approach to externalizing the query planner was to identify which set of rules make sense for a query, thus steering its search space towards efficient plans. Additionally, multi-query optimization is an important part of the query planner. In this, I refer cloud views on materializing views helped improve latency by 34%. Next, let's discuss the risks and responsibilities for building a service-oriented query optimizer architecture. Applying machine learning for building better systems has emerged as a hot trend in recent years. It is motivated by the fact that modern cloud systems have become too complex to optimize. Even though it makes sense to apply machine learning for building better query optimizers, it is well known that machine learning comes with its own set of dangers. The question is whether by applying machine learning for query optimizations, we are importing those dangers as well. Next, I discuss some critical questions. Next, we dive deep into the question, are we serving all customers or are the rich getting richer? One of the biggest risks of using machine learning for query optimizers is that customers with larger workloads benefit more, since they can train better models to make optimization decisions. In contrast, the cloud provider has a responsibility to serve all customers, and so they need to devise techniques to transfer the learnings across. Therefore, the cloud providers still need to find mechanisms to democratize Optimizer as a service for all players. Next question we ask is, are we building better systems or are our systems opaque? By externalizing and replacing parts of the query optimizer with machine learning models, we risk substituting transparent, well-understood components with models that could be hard to explain or reason about. That is, are we leading to fundamentally better systems? Next, are we helping system developers or are we giving developers a hammer for every nail? Developers can easily fall into the trap of fixing everything in the system software using machine learning, bypassing better coding and system building practices in the first place. The challenge though is that they now need to maintain both the default-based system and augmented part of it in the optimizer as a service. Here, I show the references of the papers described during the talk. To conclude, in this talk, I opened up a fundamentally new debate in query optimization to build Query Optimizer as a service. Some key takeaways from the talk are the reference architecture of designing such a service, which is in production in Cosmos at Microsoft, and the risk and responsibilities associated with Optimizer as a service which need to be introspected. Thank you.